Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over polarity, and we're going to talk about polarity of bonds and polarity of molecules. So let's get into this. So the first thing you want to keep in mind is that when you're trying to determine the polarity of a bond or a molecule, you need to know, you need to take in consideration the difference in the electronegativity of the atoms that are being bonded in the molecule. So we're going to be focusing on, our goal is to understand how to determine whether a molecule is polar or not. But the first thing we need to do is determine whether the bonds are polar or not. Because if your molecule doesn't have polar bonds, it's not going to be a polar molecule. If there are polar bonds, that may or may not be polar depending on the symmetry of the molecule itself. So you need to know the shape of the molecule as well. So in addition to knowing how to figure out the difference in electronegativity, or at least be able to determine that there is a difference in electronegativity, you also need to know how to determine the shape or geometry of the molecule. So you're going to need to know that chart, Vesper theory, and there's usually a chart that shows you the number of bonding groups and non-bonding groups and how to determine the shape of a molecule based on the number of bonding and non-bonding groups. So you'll either need that table handy or you'll need to memorize that table depending on what your teacher wants. So let's get into this. So the first thing you need to know is basically what's happening in the molecule and how the electrons are distributed in the molecule. And basically, when we're talking about the polarity of molecules, or especially the polarity of bonds, we're looking at how much the electrons are shared. Are they shared equally, or are they shared unequally? Does one atom want the electrons more in the bond or than another atom, or do they want them the same amount? So that's where electronegativity comes in. So let's look at a few molecules. We're going to start with oxygen and hydrogen. So when you form the Lewis dot structure, so you're going to need to know how to write Lewis dot structures. And so when you do the Lewis dot structure for oxygen, it looks like that. Now, the thing that Lewis dot structures don't show you is the shape of the molecules, or not necessarily the shape of the molecules. And so the thing to keep in mind here, and let's put hydrogen here as well. So if we're looking at this molecule here, so the thing about these molecules, and let's do HF2. So the Lewis dot structure of HF looks like that. And so if we look at oxygen and hydrogen first, you'll notice that this is a molecule where you have two atoms that are the same atom bonded to each other. And so in this case, both the oxygen atoms have this same electronegativity. So because electronegativity is kind of the measure of how much they're pulling on the electrons in the bond, how much they want those electrons, since both of the atoms that are bonded together are the same, they have the same electronegativity, they're going to have the same pull on the electrons in the bond. Therefore, there is an equal sharing of the electrons in the bond between the two atoms. So therefore, the electrons are not going to stay on one atom more than the other. And so we can represent this here as kind of a cloud of sorts. So you can see that the electron density, right, if I put a kind of an oval here like that, you can kind of see it's not quite right. I don't want to be too fastidious about this, but see if I can make that better. So here you can see that the electron density is equal or spread out equally among the two atoms here. So one atom is not really pulling on the electron density any more than the other. So there's no polarity here. So when you were thinking about polarity, think about a magnet, right? So if you've had experience with a bar magnet, right? So a bar magnet has a positive side and a negative side. And so we call this the positive pole and the negative pole of the magnet. So one side has a different attractive force than the other. So when we're talking about polarity in a molecule or polarity in a bond, we're looking for an analogous thing here. So here, since the electron density is equally shared, one side is not going to have more electron density than the other. So there's no plus or minus charge or partial charge on the molecule. And the same thing can be said for hydrogen here. We have two atoms that are the same atom bonded together, the same electronegativity, so they're going to be pulling on those electrons equally. So there's no unbalance or unequal sharing of the electron density. So when we look at the electron density, if we did a cloud here, the electron density would be equally distributed in the molecule. Okay, so both of these, so if we're looking at the bond, then the bond here is a nonpolar bond because the electrons in the bond are being shared equally. And so therefore we would expect that the electron density is going to be the same, shared equally between the two atoms. So because our molecule only has one bond, and that one bond is nonpolar, therefore the molecules are nonpolar as well. We'll talk about molecules that have more than one bond or more than two atoms bonded together. But right now we're focusing on molecules that only have two atoms that are bonded together. Now, let's look at HF. HF has this Lewis dot structure, and we know that the electronegativity of fluorine is a lot more than that of hydrogen. So fluorine, because it has a much greater electronegativity, is going to be pulling on the electrons in the bond more than that of the hydrogen. Therefore, the electrons in the bond are going to be spending more time over here with the fluorine than with the hydrogen. So what does that mean? That means if we draw our electron density cloud, the electron density cloud here is going to be greater, so the electrons are going to be spending more time over here than over here. So we're going to have a higher probability of finding the electrons over here. So if I was to draw the electron density of this molecule, it would look something like this. So here, the electron density is much greater because fluorine has a greater electronegativity. It's pulling on the electron more, and so you would expect the electrons to be spending more time over here or closer to this side than this side. And so what that means is that this side is going to have what is called a partial negative charge because electrons are negative. So this is going to be the partial negative side of the bond. And so since the electrons are being pulled away from the hydrogen, that's exposing more of the positive nucleus of hydrogen. So here the positive nucleus is not being as balanced by the electrons in the hydrogen atom here. And so it's going to have a partial positive. And so this little like S looking thing or cobra, if it looks like a cobra to you, this is the lowercase symbol for delta, which is the Greek symbol. The uppercase delta looks like a triangle like that. The lowercase looks like this S or cobra looking thing. So when we write this symbol here with a negative, that means partial negative. So we have a partial negative side. It's not a full charge. It's a partial charge. It's not quite an ion, but it's getting closer, right? So here we have a partial negative, and then here we have a partial positive. And there, ladies and gentlemen, is the polarity of the molecule, right? Because just like the magnet with a positive side and negative side, a positive pole and negative pole, we have a polarity here. We have a negative pole and a positive pole. And that's because of the unequal sharing of the electrons. So this is one way we can show the polarity or is designate polarities by using partial charges. Another way is to use a dipole moment arrow. So again, to say that something has a dipole moment means that there's polarity. So you can draw an arrow, and the arrow is drawn towards the negative side. So the more electronegative side, the arrow goes towards the electronegative side of the bond. The more electronegative atom, it points towards that atom. And so it's pointing towards the partial negative side. And then we put a little line here for a plus sign. So we have a plus sign here. So this side of our bond or molecule is going to be positive. And then here we have the straight line going this way, so negative. So this side of the bond or molecule is negative. This side is positive. So this is called a dipole moment arrow. And so this is showing the polarity of the bond. And again, because we only have one bond here in the molecule, therefore, since the bond is polar, the molecule itself is also polar. So I hope that is clear. So that's how you figure out the polarity of a molecule when you only have two atoms in your molecule. So again, if they're the same atom, then the electrons are being shared equally. There's no uneven distribution of the electron density, and so it's a nonpolar bond and therefore a nonpolar molecule. Here, the atoms are different. So because the atoms are different, they're going to have an unequal sharing of electrons. Now, you could have different atoms that have a very small difference in their electronegativity, and in that case, even though you have different atoms, you could have still a nonpolar bond. And so I'm thinking of carbon-hydrogen bonds that are technically different atoms, but if you look at their electronegativities, the electronegativities are so similar that the difference is nearly zero or is zero, and therefore those would be also nonpolar bonds. But generally speaking, if you have two atoms that are bonded together, they're going to have different electronegativities, and the difference in the electronegativities is going to be great enough where you do have a polar bond. But that's not always the case. So when in doubt, you can use an electronegativity table or use a periodic table that has the electronegativities on them, and then find the difference between them. And remember, if the difference between them is less than 0.5, then you've got a nonpolar bond. If it's 0.5 or greater, then you've got a polar bond. Okay, so that's for molecules that only have two atoms bonded together. What about molecules that have more than one? Like, so for example, we have water and carbon dioxide. So let's look at water as an example. So when we look at water, if we draw the Lewis dot structure for water, we get this. And so you'll see here that we have, this is our Lewis dot structure. And for this, we have two lone pairs on the oxygen and two bonded pairs here. Now, one thing to keep in mind, again, is that drawing Lewis dot structures does not indicate the shape of the molecule. So if I was to look at this, it looks like it's a linear molecule, but that would be wrong. So you should know how to figure out the shape of this molecule from Vespertherian, from the chart and the table where you look at the number of lone pairs or non-bonding pairs and the number of bonding pairs. And from there, you can look at your table and figure out what the shape of this molecule is. So here you should know that the electron group geometry of this is actually tetrahedral because we're taking in consideration all of the electron groups, and we have 4 electron groups. So that means the electron group geometry is going to be tetrahedral. But here we're interested in the shape of the molecule, the actual shape of the atoms. And there, because we have these two lone pairs, that means that the shape of this molecule, the molecular geometry, is bent. So if we have a bent molecule, so I'm going to draw that here. So I'll draw this like so, and then you could have your lone pairs there. Now, here we have our bent molecule, and so when we're looking at the polarity of the molecule, we look at the polarity of the bonds. And here I'm going to draw arrows to help you see the polarity of the molecule. And so what you're looking for is an overall polarity direction in the molecule. So you got to look at the bonds first and see which direction is the polarity going, those dipole moments, these arrows. So here I have hydrogen and oxygen. So if I'm looking at this bond here, oxygen is a more electronegative atom, and so therefore the oxygen is going to be pulling on those electrons more. So if I'm looking at the polarity of this bond, the arrow would be drawing towards the oxygen. So the arrow is pointing towards the more electronegative atom. And so that means the electrons are being drawn more closely to the oxygen here. And so the same thing with this bond here. I have hydrogen and oxygen, it's the exact same thing. So the oxygen is pulling more on the electrons in the bond. So here, sorry about that. So here you have a dipole moment with the polarity pointing towards the oxygen. So again, remember it's pointing more towards electronegative, and the plus sign means that the hydrogen here has a partial positive. So here we have a partial positive on the hydrogen, and here we have a partial positive in that hydrogen, and here we're going to have a partial negative charge on the oxygen. And so here, because both arrows are pointing in the same relative direction towards the oxygen, that means that if you add these arrows together, the polarity of the molecule is going to be going basically in this direction. And you can see that we have on this side, if we look at the oxygen, we have two sides. We have this side here, and we have this side here. So you can see that there, if you divide the molecule in half, you have polarity in the molecule. So you have a negative side, partial negative. The oxygen is the partial negative side, and you have the hydrogens, the partial positive hydrogens on the other side. So you have a partial positive side of your molecule, and you have a partial negative side of your molecule. And so you can see that by the shape of the molecule, and that these two arrows are pointing in relatively the same direction. They're pointing up. So if you were to add these together, you could draw an overall polar dipole moment through the molecule that would look something like that. So we have the positive side and the negative side. And so this would make this a polar molecule because both the bonds are polar, and also the general direction of the polarity is pointing in one overall direction. And so it gives you one side being partially negative and another side being partially positive. All right, well, what about carbon dioxide? If we do carbon dioxide, let's go ahead and draw the Lewis dot structure for that. So here we have the Lewis dot structure for carbon dioxide. And there it is right there. So one thing to notice when we're when we're trying to determine the shape of the molecule is to remember that even though we have double bonds here, the double bond is considered one group, right? So we're not counting this as two groups, it's one group, and this is one group as well. So from the Lewis dot structure and using our VSEPR theory and using that chart that's showing you the shapes of molecules based on number of bonding groups and non-bonding groups, here we is our central atom, carbon, and here we have two bonding groups. So we're treating the double bonds as one group each. So we have one group here, one group here. We don't have any lone pairs. So here is an example of a molecule with two bonding groups. And remember, the electrons in the bonding groups want to be as far apart as possible. And so they're going to be on opposite sides of the central atom. So this, ladies and gentlemen, is a linear molecule. Okay, so because it's a linear molecule, we can look at the polarity of the bonds. Again, just like we looked here, we looked at the polarity of the bonds. So let's look at the polarity of the bonds here. So here we have oxygen on both sides. So if we look at carbon, this carbon-oxygen bond, oxygen is more electronegative. So again, the electrons are going to be pulled in this direction towards this oxygen. So that's going to give this a partial negative charge. And carbon is then going to have a partial positive charge. And then we look at the other bond here. So I'll draw the arrow here. So here, again, this oxygen is more electronegative, so it's pulling on the electrons more. So this arrow, again, would be pointing in that direction. So again, we get a partial positive charge on the carbon, and then this oxygen has a partial negative charge, like so. So here we have a partial negative. So we have polarity in this bond, and we have polarity in this bond. But notice that there is symmetry in the molecule. And so why is that important? So whenever you have symmetry in the molecule, the polarity of the bonds cancel each other out. And so you get basically the molecule as a whole is going to be nonpolar. So this is the case where even though you have polar bonds, if the polarity in the bonds, if the dipole moments cancel each other out, then the molecule is not polar as a whole, even though the bonds themselves are polar. And this happens when there is symmetry in the molecule. So symmetry will destroy the polarity of the bonds, or not, I shouldn't say destroy, but they'll cancel out the polarity in the bonds so that there's no polarity in the molecule. So here's a good example of that. And so again, it's really important to know how to figure out the shapes of these molecules in order to determine whether the polarity of those molecules or whether the polarity in the bonds are going to cancel themselves out. Okay, so I did these here. Now let's look at these here. So we'll look at other examples of molecules that have polar bonds that may or may not be polar themselves. So let's try again this one here. So we have HCl. So we should write out the Lewis structure of HCl. And again, just like HF here, chlorine is more electronegative than hydrogen. So there we would have our dipole moment. The arrow is going to point towards the chlorine and away from the hydrogen. So that's going to give chlorine a partial negative charge, and hydrogen is going to be a partial positive charge. And so again here, that bond is going to be polar because we have this separation of charge in the bond. And because we have one bond in the molecule, we only have these two atoms bonded together. Since the bond itself is polar, therefore the molecule will be polar as well. So that would be an example of polar bond giving polar molecules. What about NH3? So if we write the Lewis dot structure of NH3, it would look like this. So there's our Lewis dot structure. And so again, from the Lewis dot structure, you're going to want to know how to determine the shape of the molecule. So again, we have 4 electron groups. So according to the chart and according to Vesper theory, this electron group geometry is tetrahedral, but because of the lone pair there, the molecular geometry is different. It's going to be a different shape. So here, these 3 are going to form a shape called a trigonal pyramidal shape. It's going to be a trigonal pyramidal. And so if I draw the shape here, I'll do my best. So you'll have a hydrogen there, and then a hydrogen there. Or maybe this one's going into the board a little bit. So here you have the shape of the molecule. Sorry for my drawing. But what I want to point out is that this lone pair here, this lone pair is pushing these 3 atoms down and therefore taking up space. So these 3 atoms are being pushed down towards the bottom of the molecule. So you have the nitrogen on top of your pyramid. So here's the top of the pyramid. Here's the base of the pyramid down here. And so when you look at these 3 bonds, if you look at the polarity, remember the polarity of the bond is pointing towards the more electronegative atom. So nitrogen is more electronegative. So you have this, the dipole moment of the bond pointing this way. This one again is pointing up towards the nitrogen, and this one is pointing up towards the nitrogen. And so you can see that the general placement of the dipole moments, the polarity of the bonds are all pointing up towards the nitrogen. So that means that the nitrogen is going to be the partial negative side of the molecule. And then down here you have your partial positive hydrogens. Oops. Partial positive. And so again, you can see that because all the arrows are pointing in the same regular direction because of the shape of the molecule, that means that these, the polarity in the bonds are not going to cancel each other out. They're actually going to add up. And so the general polarity, if I draw a bigger arrow, is going to go this way with the positive side on this and the negative side on this. So your molecule is going to have a partial negative side, and on this side is going to have a partial positive side. So it's got that polarity in the molecule. So this is an example again of where you have more than 2 atoms bonded together, and you've got polarity in the molecule itself because the bonds are polar and the overall shape of the molecule is such that the polarities do not cancel out. They actually go in one particular direction. And so you can determine that this would be a polar molecule. And so you can now see that. But then what if you have polar bonds? You can have polar bonds and still not have a polar molecule. So I will continue this in the next video. So if you like my videos, please hit that like button there, subscribe to my channel, hit that notification bell up there so you can be notified by other videos I put out, and put a comment down in the comment section. Let me know what you think. Thanks for joining me. Have a great day.